Now, talking about a few classic integrals, of course, these are some things which, if you see in your equations, you must write down the answer directly. So, let's say if you have integration of e to the power x, and this is entirely multiplied by f of x plus f dash x, then you can directly write down the answer as e to the power x f of x. Now, in this question also, if you looked at this question carefully, can you see that we have f of x here? And is f dash x similar? No, right? That means you couldn't have applied that formula here. So keep this thing in mind. And here also, let's say there's a bracket missing here. This would be under bracket. So let's say if you have a x multiplied by f dash x plus f of x, then also you would get simply x f of x as your answer. So keep this thing in mind. Whenever you see such type of function, you must directly write down their answer. Let's look at this question. If integration of this dx is equals to e to the power x f of x. Now, here what you can see is that this integration I'm getting e to the power f of x. Now, when did I used to get e to the power x f of x? It used to be when e to the power x used to be multiplied by f of x and f dash x, right? That means this entire function would somewhat be transformed into this format e to the power x. Something I should have as f of x plus f dash x, right? So I'll try to convert this x square plus 1 upon x plus 1 whole square into this format only. So what can I do? I have x square plus 1 upon x plus 1 whole square. So what I'll do is in this entire function, I'll simply add a 1 and I'll subtract a 1. So what would I get? I'll write it down as x square minus 1 plus 2. And I'll consider these to be two different terms. So I would have x plus 1 whole square. And here I would have x plus 1 whole square. Now here from here what I'm getting is this would become x minus 1. X square minus 1 can be written as x minus 1 into x plus 1. X plus 1 and x plus 1 would cancel out amongst each other and I would have left x plus 1 only here plus 2 by x plus 1 whole square. Now if you look at these two functions which have been separated, x minus 1 upon x plus 1, this can be taken as f of x, and 2 by x plus 1 whole square. Isn't this the differentiation of x minus 1 upon x plus 1? Yes, it is. Let's say if I was to show you that differentiation, x minus 1 upon x plus 1. If I try to differentiate it, of course, in the denominator, I would first have this square. I would have differentiation of first function, which is x minus 1 would become 1. Second function as it is, minus first function as it is, differentiation of second. So from here, x and x would cancel out, and I would have 2 by x plus 1 whole square. So basically, this is my f dash x, and this function here is my f of x. So now that I've gotten my f of x and f dash x, that means I can directly write down this integration as e to the power f of x. So what does my f of x become from this equation? X minus 1 upon x plus 1. So this is my f of x. Now what has been asked to us in the question? We need to find out the triple differentiation or the triple derivative of f of x. So let's differentiate it one by one. So first we'll have f dash x, which would be 2 by x plus 1 whole square. Then what would be our second differentiation? It would be 2 upon x plus 1 cube, and we would have a minus 3 multiplied as well. And what would be our triple differentiation or third derivative? It can be written as minus 6. This would become 1 upon x plus 1 to the power 4, x plus 1 to the power 4, and here we would have a minus 4 multiplied as well. So minus and minus would cancel out amongst each other. We would have 24 by x plus 1 to the power 4. Now, what was asked to us in the question? We have found out our f triple dash x. Now we had to find out its value at x is equals to 1. So I'll simply put x is equals to 1 in this function. So I would get 24 by 2 to the power 4. So upon simplifying this, what am I going to get? This would become 3 by 2. So this is our answer. So this is how you can find out your functions when you can see that there is any type of classic integrals, any of this is present. So now talking about a few more classic integrals which you need to remember. Let's say if you see integration of e to the power ax into sine bx dx. Simply directly you can write down your answer as e to the power ax upon a square plus b square into a sine bx minus b cos bx. Now the same thing when you have cos instead of sine. The entire equation would be same. The only thing is that sine would be changed to cos and minus sign would become plus sign and cos would become sine. So you must remember the replacements. Do not confuse yourselves among these two. Remember the formulas properly. If let's say you're not being able to remember the formula properly, what you can simply do is apply your by parts here. So if you would apply your by parts, this trigonometric function would become your u because it comes higher in priority, and this would become your v. And based on this, you can solve your question. Now, a few more formulas that we must remember. I hope you all remember in the start, while studying substitution, we had done one question, which where we had received 1 upon, sorry, dx upon t minus something whole square, minus something whole square, right? There I had told you that we would learn about this formula later. So here you can see the formula has been applied here. So there, if let's say I have t minus 5 by 4 whole square, so this entire term would be considered as my x. So this would become x square minus a square, whatever is there. So instead of x, I would replace the value as t minus 5 by 4. Simply, if you see such type of functions, you can directly write down your answer as 1 by 2a log of, here the base of log is e. So keep this thing in mind, it is ln. If you have x square plus a square, it would become 1 by a tan inverse x by a. If you have these type of function, of course, you can write it down in this way. So remember all these formulas. It would be helpful for you to solve different integrations. Here are a few more. Let's say if instead of the denominator, you have such type of functions in the numerator, then how are you going to solve it? As I had told you earlier, of course, if you do not remember this formula, what you can simply do is you can substitute your x as a square, sorry, as a sine theta, sorry, sine theta, or a cos theta, or a tan theta, depending on what type of function you have, so that this entire square root portion can be removed. And then based on that, you can write down your answer. So keep this thing in mind. However, I would recommend that you remember all these integration formulas so that it would become very easy for you to solve questions during examination. It wouldn't take much time for you to solve any type of question which is given. So now let us look at this different type of integrals. Let's say if in the question you have some integration of this format, these three formats, where you have a quadratic given, be it inside the root, be it in the denominator, or be it in the numerator. What you can see is what would their differentiation be? Their differentiation would be 2ax plus b, right? So I'm going to write my px plus q, which is in the numerator, my linear function. I'm going to write it in this format, lambda of this plus mu. And then I'm going to find out my lambda and mu. Then what I can do is I can separate this function out in two different terms. So basically I would be able to write this entire function as lambda of 2ax plus b upon ax square plus bx plus c, plus this would become mu by ax square plus bx plus c dx. So here you can see that this is my quadratic equation and I have its differentiation on top. So I can assume this to be t, and of course dt would become my this differentiation dx. Here I have a quadratic equation below. I'll try to convert it into a perfect square, and then I would use the formulas that we had studied. So this is how you have to solve such type of integrals. Let's look at one question so that it would become much clearer to you. Let's look at this one only. So you can see we have a linear upon root under quadratic. So what am I going to do? First, if I look at the differentiation of this quadratic, what is it going to be? 1 minus 2x, right? So I'm going to assume that my 7 minus 3x is equals to lambda times of 1 minus 2x plus mu. Now I'll find out my values of lambda and mu. So what would my lambda become? My lambda plus mu would be equal to 7, and my minus 2 lambda would be equals to minus 3. So I would get my lambda to be equals to 3 by 2, and from here I would get my mu to be equals to 11 by 2. So I've gotten my values of lambda and mu. Now what I can do is I can replace it in instead of the linear function. So I would have lambda, or I'll just write it its value only 3 by 2, 1 minus 2x upon root under 8 plus x minus x square, and I would have a plus 11 by 2 root under 8 plus x minus x square dx. So from here, what I can see is that in my first term, I would have 3 by 2 outside. Of course, what I can do in this function is I can assume my 8 plus x minus x square to be t. So if I assume my 8 plus x minus x square as t, what would I have? I would have 1 minus 2x dx as dt. So this would become my dt. That means in my integration, what am I going to have? Dt upon root t. And it is very easy for me to find out the integration of this. So this would basically transform into, let me write down the answer directly. So this would become 3 by 2 3 by 2 integration of dt by root t. And here what am I going to have? I'll take 11 by 2 common. And inside what I can do is I can take minus common for a moment. And this would become x minus half whole square plus this would become, sorry, this would be minus root under 33 by 4 whole square. So here I have x square minus a square. So if I find out its integration as per the formula that we had studied, so what would our final answer become? 11 by 2 sine inverse of x minus half upon root under 33 by 4. This is what I'm going to get from the first this function. Now from the second function, what am I going to have? I'm going to have 3 by 2 root under 33 by 4 whole root under. If you remember the formula that we had studied earlier, this would basically become 1 minus x minus half, sorry, this would become 1 minus x minus half upon root under 33 by 4 whole square. Wouldn't this be the answer that I'm going to get? Plus, there would be a constant of integration c as well. So again, I hope you must have understood how we can solve integrals of this format. It is very easy for us to solve. Again, find out its differentiation, find out your values of lambda and mu, separate it out, and then you can use our previous formulas that we've already studied. Based on that, you can find out your answer. Now again, a few more portions of such partial fraction. This type of integrals, what we call it as, this method we call it as the partial fraction method. So here are a few more ways of doing our partial fraction. What we can do is, let's say if I have px plus q upon x minus a, x minus b, we can separate it out in two different terms, a by x minus a, b by x minus b. Similarly, for all other these five rational functions. So keep this thing in mind. It would be helpful for you while solving questions. Now you must be thinking, how are we going to find out the value of capital A and capital B? So of course, if you take the LCM, of course, below you are going to have x minus a, above x minus b, and you would have a as x minus b plus b as x minus a. So simply what you can do is, for a, what would be your values of a plus b, you can call that as p, because these are the coefficients of x. The coefficients of x are going to be a and b. So this is how you can write it down. And then a minus ab minus small a capital B, this would be equal to q. And a and small b are known values to you, so you would have two variable, two equations. You can find out your capital A and capital B. So you can write it down in this partial fraction format. Whatever type of whatever type of rational function has been given to you can be written in this format. So keep this thing in mind. Let's look at this question based on that properties only. So here what you can see is I have 2x dx on top. I have x square plus 1 and x square plus 3 below. So simply what I can do is I can assume my x square to be t. This would become 2x dx is equals to dt. So I would have in my integration dt upon t plus 1, t plus 3. Now how can I write this down? This can simply be written as 1 by 2 times of 1 upon t plus 1 minus 1 upon t plus 3 dt. This is how it can be written. Now if I integrate this, what am I going to get? This would become half of ln t plus 1 upon t plus 3. This is what I'm going to get, plus c. So now upon substituting the value that I had assumed t to be, it was x square, right? So if I substitute its value, I would get half of ln x square plus 1 upon x square plus 3 plus c. This is what I'm going to get. Now they've told us that f of 3 is half of ln 5 by 6. So basically they want to tell us what would be the value of c. So f of 3. So let me find out f of 3. This would become half of ln 3 threes are 9, so this would become 10 by, here we would have 9 plus 3, 12 plus c. So basically this is nothing but 12 ln 5 by 6. So this is what exactly was given in the question, right? That means our c would become equals to 0. So our final function f of x that we've gotten, it is half of ln x square plus 1 upon x square plus 3. This is what our final function is, right? Now from this final function, we need to find out the value of f of 4. So simply we'll put x as 4 in our equation. We would get ln of 17 upon 19. This becomes our answer. So this is how you can solve questions which are related to partial fraction. Now here in this question, of course, we did not need any such concepts of a and b. Let's say if you weren't able to distribute this as 1 upon t plus 1 minus 1 upon t plus 3, then you can use this format which we had studied, a upon x minus a plus b upon x minus b. So keep this format in mind. Now here are a few more formulas that you need to remember. Now these are integrations which go on forever. Like this would go on up till a series. So if we have integration of sine to the power nx, again we would have minus 1 n. So what we've done here is we've integrated it. Now keeping in mind that our by parts function. So if we keep our by parts function in mind, then we would have this type of equation come out. And then we would have this integration left out. Then if we integrate this even further, we would get one more equation where we would still have an integration where sine would be to the power n minus 4. So keep this thing in mind. Such type of series you can get during your questions. So you can directly write down using the values of n that have been given in the question. So keep all these series in mind as well. If let's say you do not remember this series, of course, you can use your by parts anytime and in any question given to you. Now, if I was to talk about a few more different types of integrations, let's say if you have integration of dx upon a plus b sine x, let's say, or you have integration of dx upon a plus b cos x, or let's say if you have both a plus b cos x plus c sine x, or any type of such functions. Let's say if you have where you have the single power of sine, you single power of cos, how are you going to solve this question? If you see such type of questions, what you can do is simply replace your sine x as 2 tan square, sorry, 2 tan, there wouldn't be 2 here, 2 tan x by 2 upon 1 plus tan square x by 2, and cos x can be replaced by 1 plus tan square x by 2 upon 1 minus, sorry, we would have plus minus on top, plus below, tan square x by 2. Simply replace sin x and cos x in this format. Now in your entire function, you would simply have just 1 minus tan square x by 2, 1 plus tan square x by 2. 1 plus tan square x by 2, what you can write it down as? You can write it down as sec square x by 2. And sec square x by 2 dx is basically the differentiation of tan x by 2. So simply what you can do after this is put here tan of x by 2 as t and then solve the question. So it would become fairly easy for you. Now, such questions are to be solved only and only when you have cos and sine functions in the denominator. If let's say it would have been in the numerator, then it would have been solved by either separating out the different terms or by using the by parts function. So keep this thing in mind. And sometimes what would happen is, let's say if there is a very difficult type of function given to you, in their denominator, you would have sine square x, cos square x. So what you are going to do for such type of functions is simply divide by cos square x and then put tan x as t. Again, you would get somewhere in your function sec square x, which can be written as dt. I hope you are getting it. So this would, you would have to identify what type of question has been given to you. And based on that question, you would solve your question. So keep these things in mind. Let's look at a question based on this concept. Let's say if I have integration dx by 3 plus 2 sine x plus cos x. Now here you can see that this is not an indefinite integration. This is basically a definite integration because they've given us limits from 0 to pi by 2. So how are we going to integrate it? Again, as I mentioned, we are going to assume our sine x to be 2 tan x by 2 upon 1 plus tan square x by 2. And we would have our cos x as 1 minus tan square x by 2 upon 1 plus tan square x by 2. So basically, our entire function would transform in this format. This would become 3 plus 2 tan x by 2 upon 1 plus tan square x by 2 plus 1 minus tan square x by 2 upon 1 plus tan square x by 2. Now here what I'll do is I'll assume my tan x by 2 to be t. So I would have 1 by 2 sec square x by 2 as dt, right? So from here what I can see is 1 plus tan square x by 2. What is 1 plus tan square x by 2? It is sec square x by 2. So I can take this in the numerator by taking the LCM ultimately. And then, of course, I can replace my tan x by 2 with t and dt. So I would again have a quadratic function, maybe a linear by quadratic, and then you can solve it using the perfect square method or the formulas that we've already studied. So you can solve this question also in that format. I'm not going to solve this question of the same format again. This was just for you to understand. I'll just write down the answer. You can check it after solving it by yourself. So the answer for this question is tan inverse 2 minus tan inverse 1. So basically the answer becomes tan inverse 2 minus pi by 4. So keep this thing in mind. Solve this question by yourself. If you are not being able to solve it, try to look at the previous lectures where we had studied about having a quadratic below, making it into a perfect square, and then using the formulas that we studied. Now, talking about a few more different type of substitutions that you need to keep in mind. Let's say if I have 1 by a linear into root under linear. So I can assume my linear to be t square. Now, the linear which is inside the square root, that would become my t square. So keep this in mind. Quadratic into linear, again, my linear would be written as t square. And if I have dx by root under quadratic and I have a linear outside, so I can substitute my linear as 1 by t. Now, sometimes in these type of questions, what also you need to keep in mind, sometimes you can also replace your quadratic as t square. However, that would depend on the question that has been given to you, but generally it is of this format only. So keep these things in mind. Now here are a few integrands whose integrals cannot be found because whenever I differentiate any type of function, I would never get such type of function only. So keep this thing in mind. If you find such type of integration, let's say in your question, then of course you directly have to write it down as you would find no solution for such integration. So your solution, number of solutions would become 0. So if you remember all these integrations, it would be easy for you. Else you would start applying the by parts in this entire function, keep on solving it. So to save yourself from that time, it is better you remember all these things. So that was all about the theory portion mostly and the practice of uh, all different type of questions that can be asked from indefinite integration. Now we'll be looking at a few previous year questions that were asked, and you will see that all questions are based on the concepts that we've already studied. The only thing that is important in this chapter is for you to practice it a lot, and secondly, to remember the standard integrations or the classic integrals that we've studied. Then and only then you would be able to solve the questions very easily.